This is Pralit Patel presenting from Pacific National Laboratory, Pacific Northwest, presenting GCAM, which is just a model of the world, essentially, focusing on climate. Yeah, take it away.
Great. Yeah, so good morning or afternoon. I am Pralit Patel, a computational scientist at the Pacific Northwest National Laboratory. And so today, yes, I will be giving a seminar on the Global Change Assessment Model, or GCAM, on behalf of the entire GCAM development team. And so what I hope to describe is kind of the research niche that GCAM serves, and then finally move on to explore the questions that can be answered, and also the questions that we're exploring next. Okay, so to lay this presentation out a bit further, I'm going to start with a high-level overview of GCAM. Then I'll get into some background about where in the climate change research modeling community this style of model fits. I will talk about our sponsors and how that drives our research agenda. Then I'm going to bounce back into modeling details so that you're not just left with an abstract notion of what this does. And finally, end on some examples of what can be done and hopefully tie it back to some experiments that are more germane to your areas of work or research. And so I've got a couple of natural spots in here as I'm bouncing back and forth for questions, but I'm also amenable to take questions at any point in time. I'm trying not to delve too far into the details, but maybe someone's interested, so feel free and stop me if you want to ask a question. All right. So GCAM's strength is that it represents several human Earth systems all together, modeled together in an integrated and consistent system. It will not have the most processed details of any of these systems, but it does have global coverage, and different systems are modeled at different spatial resolution. The energy economy are typically modeled at the 32 geopolitical regions. Water supplies and demands are balanced at 235 major river basins. The agriculture and land then is the intersection of the geopolitical and water basins, which yields 384 regions. I will note that we do have versions that further subdivide a region subnationally. So for instance, we can split out the 50 states of the US or the provinces of China. We also have collaborators that are doing this in India and China, or Canada as well. Also coupled in GCAM is a reduced form Earth system emulator called Hector. It produces global greenhouse gas concentrations, forcings, and global mean temperature anomaly that can be tuned to mimic the behavior of an Earth system model, or ESM. It's kind of quick aside, I will try to be sure to spell out any acronyms, but apologies if I miss any. GCAM has explicit characterization of energy and agricultural technologies. It will combine historical data with a number of user assumptions, which I'll touch on in a second, and will simulate into the future through the year 2100 in 5-year time steps, producing a number of outputs, including emissions of 24 greenhouse gases, which of course are fed into the simple climate model. Finally, GCAM is open source and available on GitHub, where you can find the C++ source code, as well as an R-based data processing system, which will generate all of the inputs that you need to run the model out of the box. Okay, so here's a figure illustrating at a high level and is not comprehensive which model assumptions we have to adjust to get different scenarios in the future, such as what is the population and GDP projections, what is the cost of a wind turbine in 2065, for instance, and of course, the imposition of some sort of policy, such as if we wanted to mitigate climate change in the future, for instance. The model equations are, well, they're mostly macroeconomic statistical equations. such as logit-based discrete choice functions or price and income elasticities to drive demands. And the results we can get out are emissions, prices, supplies, and demands of various goods, such as oil, gas, coal, electricity, corn, wheat, bioenergy products, as well as global or regional land cover. Given these parameters are highly uncertain, we need GCAM to be computationally efficient, as we need to run as many scenarios. Well, we will need to run many scenarios to get a solid understanding of insights being provided by the simulations. Of course, computationally efficient is in the eye of the beholder. At this point, GCAM takes about half an hour to run a simulation all the way through to 2100. Again, I will be going into more detail about the modeling later, but maybe at this point you're getting a broad understanding of what GCAM can do. Before I bounce back into background and research, I want to mention some other models which we have also developed that are not GCAM, but are in what we call the GCAM ecosystem. I should note that for each of these models are also open source and have their own repositories on GitHub. They are also described in open access literature in more detail. I'll just briefly describe what these are, and maybe later it will become clear why they are useful. The data development tools, the GCAM data system, and Mirai handle harmonizing data products from a wide range of sources, such as IA energy statistics, the FAO ag statistics, or gridded land products. And then they combine them with user assumptions to produce all of the inputs to run GCAM. Hector, I've already mentioned. Xanthos is a simple hydrology model which processes historical and future Earth system projections to provide runoff and renewable groundwater availability constraints to GCAM. Demeter downscales GCAM land use results to half-degree grid cell. Tethys downscales water use results to half-degree grid cell, and it also applies a seasonal distribution. FieldGen emulates ESM spatial and temporal patterns to translate global mean temperature to gridded temperature and precipitation. FieldGen also emulates FieldGen emulates process-based crop models to give crop yield responses to changes in global CO2 concentration and local temperature and precipitation. So in other words, Persephone is reliant upon either Earth system model output or FieldGen output. Okay.
Let me actually ask about that one. The statistical downscaling. Are you going to come back to that? Because that sounds like an interesting thing about making local predictions from global analyses.
Yeah, I will come back to that in the end. I don't know. I mean, I'm also happy to answer some questions now, or
let's just let you find out how that works.
Okay. So I'm sorry. Did you want to hold off the question, or do you want me to
hold off? Like whenever you get to it, that's a good time to ask this question.
Okay. All right. Any other questions from a high level about what is GCAM or what does it do before I transition a little bit here? Okay, so I'm just gonna move on and change gears a little bit and fill in some background about where GCAM fits in the climate change research community. GCAM's roots actually goes back to the 1970s. With the Edmonds-Riley-Barnes model, which was just an energy system model with a pretty simple representation of major fossil fuels. It has come a long way since then in terms of scope and detail. It is a handful of integrated assessment models, or IAMs, from around the world, which have been providing scenarios of climate change futures and potential pathways to mitigation since the very first IPCC assessment report. So the IPCC is the Intergovernmental Panel on Climate Change. So I want to say circa 2008, the climate modeling community wanted to harmonize around future emissions scenarios. So the IPCC created the Representative Concentration Pathways process, which they selected a different integrated assessment team to generate a particular climate forcing target scenario, which spans a wide range of climate futures. And so the GCAM team was selected to produce the 4.5 watts per meter square representative concentration pathway, or RCP. The Earth system model results from this RCP process has been hugely beneficial to the IAM community in return as well, as it has enabled the first round of incorporating climate feedback, since we can match future climate scenarios, and mine ESM results for the basis of climate feedbacks or emulators. However, this is just one scenario to produce that climate future. Obviously, given all of the possible parameter assumptions I discussed earlier, there are many ways to get to 4.5 watts per meter squared, for instance. So, having additional quantitative scenarios was clearly needed for other modeling communities, such as those interested in studying climate impacts or vulnerabilities, which need additional context besides just climate futures. So we were involved in planning and producing the Shared Socioeconomic Pathways, or SSPs, which was meant to fill this gap. Similar to the RCPs, it spans a wide range of possible futures. However, these futures are storyline driven along two axes: challenges to adaptation and challenges to mitigation. And it was the job of the integrated assessment models to translate these storylines into quantitative scenarios. So that we have these 5 storylines, and each of these could be run for each of the RCP targets, matching storylines with climate futures. So these are just a couple of the important examples of how this style of modeling has been useful to the climate modeling community more broadly. Now I'm going to move on to who are our sponsors and what sort of research do they fund us to do. And so our primary sponsor is the United States Department of Energy Office of Science. And so they support us to do basic science, fill in gaps in research and or modeling capabilities to better understand the potential and risk of climate change. The previous examples of the RCPs and the SSPs were in line with the Office of Science mission. We do have other US government sponsors who are interested in more applied research, such as the US Environmental Protection Agency, who may be interested to use our work to quantify some policies that they may be considering. And finally, there are a host of non-government sponsors as well, and they might be interested in, for instance, evaluating specific countries' plans for mitigating or adapting to climate change, or understanding the value and role of a specific technology in its ability to mitigate climate change. Okay, so GCAM's home institute is the Joint Global Change Research Institute, which is primarily a part of the Pacific Northwest National Laboratory.
Sorry, can I ask a question on the previous slide?
Yeah, let's go back.
I wanted to know the non-governmental partners, what kind of services or partnership you have with them?
So
like the World Bank or Exxon? Yeah.
So almost exclusively what they want us to I should say they want us to some of these sponsors want us to provide academic reports. So they want us to explore maybe some different costs of biorefineries and understand how that increases our ability to mitigate climate change. Other sponsors are more interested in us providing modeling capabilities to institutions in developing nations so that they can have more tools to plan or or evaluate their options for mitigating climate change. Does that help?
Yeah, thank you.
Yep. Okay, so yeah, the Home Institute where the bulk of the GCAM development occurs is the Joint Global Change Research Institute, or JGCRI, which is primarily part of the Pacific Northwest National Laboratory. But it is located at the University of Maryland in College Park, which is just outside of Washington, D.C. There's about 50 staff ranging from senior scientists to more early career folks, such as postdocs, postbacks, and even undergraduate interns. We are an academically focused institute, not a consulting shop, and it has a university feel, a mentorship ethos, and some of our staff will have teaching duties as well through their joint appointments with the university. So it's a pretty diverse group, by which I mean academic backgrounds, but also personal backgrounds. Both are true. As you can imagine, when you're building a cross-cutting model as GCAM, you attract a wide range of disciplines, which I've summarized down here. Okay. And finally, GCAM has a community of users and developers outside of the Joint Global Change Research Institute. As I'd mentioned earlier, GCAM is fully open source and has been for a decade now. In that time, we've developed connections with folks from a number of universities and institutions from all over the world. It has fostered, important collaborations that have been ongoing for years. It's, having an open source modeling community has been really great for our, kind of the scientific endeavor. Okay, so I guess at this point I was going to switch gears back into some of the more gory details about the modeling itself. Were there any questions about kind of where GCAM fits in the modeling or climate change community? Okay, so then I will go into some more details. GCAM is a market equilibrium model, meaning that for the most part, individual systems communicate to each other through markets, where there is an explicit price for each market and different components will add supplies and demands given that price. The solution mechanism is then going to adjust prices at each model time step to balance all supplies and demand simultaneously. The economic activity, think GDP and population, sets the scales for demands, and emissions are a byproduct of the system, unless we are running in a mode where we are explicitly constraining some climate variable, in which case we feed back into the system where we enforce that constraint, typically by using some sort of pricing mechanism. Clearly, there are many ways that climate should feed back into the system, which is why the arrow pointing back in is declared under development. But we do have some examples of this, and a lot of the research frontier in this space is kind of where I'll be getting into in a little bit. Okay, to further describe how supplies and demands are calculated, we'll look at the energy system as an example. And so the very first column here on the left is responsible for setting the supplies. Now, I know that the arrows are drawn across. That's not really the way that it's modeled, but it is kind of the way that energy flows in the energy system. So the level of supply is going to be defined by a long-term supply curve, which is the result of a technical analysis of long-term resource availability, how much resources in the ground, for instance, and the cost that it would take to extract them. And that's the cost using current technology. And we will have assumptions of how costs change into the future, which is modeled by some smooth rate of technical change. It is similar, but not entirely analogous for wind and solar, for instance, For those, they are built up from a gridded analysis of the quality of wind resources, for instance, distance to population centers, and it's quantified in terms of then costs and capacity factors that are sorted from best to worst. Implicitly, GCAM assumes that you will build on the best locations first and progressively use up those classes until you get into the more the lower suitable locations. So in either case, you have these upward sloping supply curves, where as you increase the price, you get more supply. On the I'm going to jump over to the last column now, the far right. So the end-use sectors. The end-use sectors set the scale for energy demand, mostly by using some elasticities to relate responses and change in prices or GDP and or population. So the transportation sector, for instance, will also have a notion of speed for the different modes of transport and a concept of time value, such that as you get more wealthy, you would value your time more and switch from slower modes to faster modes, bike to car, trains to airplanes or high-speed rail. The building sector also has other important demand drivers besides just population and GDP, such as heating and cooling degree days, which is one of the opportunities that we have to feed climate impacts back into this model. So to put it a bit more concretely, maybe if you get more wealthy, you're inclined to install an air conditioner, but you would not be more inclined to run it more frequently beyond some comfortable temperature. However, as it gets hotter outside, you would be inclined to run it more frequently to maintain that comfortable temperature. So then the final demands, as we kind of move from the right up, to the left up the energy system, will choose between various final energy carriers, such as direct use of natural gas for hot water heating, for instance, or it might choose an energy carrier that has already been transformed in some way, such as electricity. Note that it's not depicted in this high-level figure, but underlying these choices are detailed technology, which is explicitly modeled in GCAM. So as we continue moving from the final energy carriers to the energy transformation sectors, these will also be choosing between different fuel options based off of relative prices of those fuels, plus the capital investment costs. A nuclear power plant, for instance, would have a high capital cost but low fuel cost, and a natural gas-fired power plant would be the opposite. It would have low capital costs but high fuel costs. Each piece is explicitly modeled and have their own rates of technical improvement, potentially lowering their costs into the future. So I've mentioned choosing between different options. And so choice in GCAM is not a winner-take-all function, and GCAM is not an optimization model. Instead, it takes a probabilistic approach, which implies there is some distribution of technology costs and or other factors. Share is based on the probability that a technology has the least cost. And we can see it is possible to get some share from multiple options depending on the shape of the distributions. Note, we are calibrating. We do have some calibration parameter here that we call a share weight to ensure that we match history. And so implicit in this calibration parameter is that all non-cost-driven factors are implicitly pulled into this one parameter.
So this is, my understanding, fairly standard model where you take the optimal behavioral science model. You take the optimal value, you put a probability distribution on top of it, and then sample from it. Like you pretend people sample from that distribution, right?
That's right. Mm-hmm.
Now, I know there's other models like K-level models and so on that try to approximate how people really think. So, what was the decision for how you approximate behavioral decisions?
Yeah, I'm not necessarily the best person to answer this question. Um, yeah, yeah. I don't know. That's best question for our, kind of the economists.
No, that's fair, and I
Yeah.
know it's a tricky one here. Okay, the way we can push it off to later because there's a whole area behind choosing the right one. At least you guys have chosen the bounded rationality model as opposed to just optimal, which is not realistic.
Right.
Yeah. Okay.
Yeah. Okay. So the demands for agricultural goods are fairly analogous to the energy system. However, the supply is quite different. Here we are explicitly modeling all uses for land cover in this nested structure, choosing between different uses, again using logit choice, but this time on profit rates instead of costs. Note that for exogenous land leaves, we have some implicit profit rate which gets calibrated in. The profit rates for crops depends on the price for the good, as well as costs such as fertilizer, which is produced, whose production is then tied back to the energy system. Um, we can see many opportunities here for climate feedbacks as well, such as yields, carbon uptake in forest, or the having the water available to run your irrigation systems. Let's see. As I mentioned before, we employ a numerical solution algorithm to adjust prices of energy, agriculture commodities, water, etc., such that all supplies and demands are balanced simultaneously. We model these one model period at a time. So we have a time step in 2050, and so how we think about 2050 is the single year 2050 that is representative for that 5-year span. We solve one model period at a time, and we carry forward information about long-lived investments, such as in refineries or growing forward, which then influences decisions in the next model period. Okay, so that's I'm gonna just skip on to some future directions here, but yeah, were there any other questions about any of those details, modeling details that folks were interested in?
Well, one thing is how you manage the interactions between different domains. Like, what was the details of that model?
Yeah, so let's see. I don't have a great figure here to show that. There are definitely linkages between the different models. We can, water is pretty clear that you have water that's used in the agricultural system for irrigation, but you also have water that's used in the energy system for a number of processes, such as for cooling use in power plants, just in industrial uses. It's also going to be used for domestic purposes for primary energy production. So that's one of the mechanisms that's cutting across each of the systems. The biggest link between the agricultural system and the energy system, I mean, fertilizer is one of those, but when you're undergoing drastic climate mitigation scenarios, the role of bioenergy, which is a land-based fuel, a renewable land-based fuel system that's grown in the agricultural system and used in the energy system. And the reason why it plays such a key role in climate mitigation is because it can be a net negative source of fuel because it's sucking carbon out of the atmosphere as it grows. And if it's used in the energy system in conjunction with a carbon capture and storage, you have a net negative system.
Okay, so how do you communicate? I'm trying to think, like water, let's use that one. You have many world regions, and each one of them has a different amount of water depending on their rivers. Do you account for, and maybe there's some accessibility of the water, because if you have a dam, very accessible. Other things, not so much. How do you account for that?
Right. So this is where the market-based system comes into play. So as I mentioned, we have this simple hydrological model, Xanthus, which is handling, runoff calculations and reservoir, and so that's going to set, kind of set the supply in some specific basin. Here's how much water is available. There's also going to be fossil groundwater curves, so that's going to you can pump that out, and that's going to be constrained as well. And so that's setting the supply. And then the demands are going to come along for the ride. For instance, here on this land system, we see that we have, for 14 different crops, such as, say corn, you could have irrigated corn, and that's going to need to pull water out of that river basin to irrigate corn. And so you'll have, the agriculture system adding demands for that water. You'll have the energy system adding demands for that water. And they'll choose based off of some price of water, how much they're going to demand. And so as the water becomes scarce, we'll increase that price such that the choice shifts to either less water intensive crops or rain-fed crops to some point, as long as, of course, that there's the yields for rain-fed crops are suitable. In the energy system, in the extreme cases, maybe you'll switch your power plants to dry cooling. Does that help?
That does. And like probably the last one on this topic is, how do you arbitrate? Like you have a market. So how does a market work? How do you do you have bidders and like agent-based kind of thing, or is it some other algorithm for figuring out the stable fixed point between the supply and demand?
So it's not quite agent-based. It is, this is where the distributions come into play, that, you'll have different technologies that are, that have different water intensities. And so they'll have different, they'll be shifted differently on this curve. And so as the price of water goes up, you could imagine the distribution is shifting over to the right, such that they get less market share, ultimately leading to less demand. And so that's on the demand side. On the water side, as the price changes, we have these supply curves, and so these are pretty. They're pretty straightforward in that you look up a price on a curve, and it says this is how much resource you have available. And so, for instance, with the groundwater, it's based off of the depth that you need to go down, and that's corresponding to some amount of energy that you need to pull that water up from that depth. And so if the price of water goes up, you'll be willing to go further to get at even greater quantities.
Okay, no, that makes sense.
Okay. Any other questions? All right, so I'm gonna move into kind of future research directions, which we're really excited about. So, and hopefully we can also tie this back to some machine learning or artificial intelligence. And so let's see here. I'll start with an abbreviated mission statement for what our next phase of long-term research plan is, which is to improve the understanding of complex interactions among water, energy, climate, socioeconomics, and other important human natural systems so that we can better capture the coevolution of the human Earth systems. So that's a mouthful, but we know that climate change is going to have long-term effects that change the nature and frequency of extreme events. Thus far, studies have not taken this into account when they're producing scenarios of the future, or they've only taken one of these feedbacks into account at a time. We want to not only understand whether these impacts have compounding effects, be it exacerbating or attenuating, but we also want to know or understand how investments or changes in human behavior can exacerbate or attenuate these impacts over a number of key metrics. So, I've kind of highlighted a few of these potentials, such as flooding, droughts, wildfire, heat waves. And so how can we get at these influences in GCAM? I've highlighted a few times throughout this talk some of the mechanisms by which we can incorporate climate feedbacks and how they might manifest in the GCAM simulation, but I haven't elaborated at all how we can dynamically predict these climate extremes when we only have a reduced form climate emulator coupled to GCAM. This is where the models in the GCAM ecosystem come into play. A full Earth system model would have all of the dynamics to get these extremes and or variability, but of course they are computationally expensive to run. A single simulation, single century-long simulation could take, a month. However, we can use our statistical emulators, such as FieldGen, to generate realizations of gridded temperature fields by randomizing, residual pattern scaling temperature outputs from any single Earth system model, retaining its spatial and temporal variance and covariance as well. And so, to kind of bring this home, does artificial intelligence or machine learning help, or is it applicable for this style of modeling? And of course, the answer is yes, but we're just beginning to incorporate these techniques. So one of the places where it is used is to train our emulators. So for instance, Persephone, our crop model emulator, we feed in gridded crop model results from this study, the Agricultural Model Intercomparison and Improvement Project, which includes over 50 crop models. And each of them ran 99 sensitivities that encompass the range of the RCP climate scenarios. And so Persephone uses all of this data to train on and create a yield response function to predict crop yield changes in response to climate change. So I have on this slide here, predicting rare events, but maybe this doesn't strictly qualify as machine learning. So the general idea here is that we only have a handful of Earth system models and RCPs, and certain conditions such as multi-year droughts are relatively rare. Therefore, we do not have enough data to accurately predict or create a probability distribution of these events. However, we can use FieldGen to create thousands of realizations of ESMs, which is mimicking its spatial temporal variability. And we can use that to generate these probability distributions. And so, kind of the last bullet here is that we want to do, thousands to millions of permutations of these climate impacts by, randomly sampling these probability distributions where we have them, or just simple permutations of other key assumptions such as the SSPs, saving only, key metrics such as global mean temperature, prices, and using some machine learning algorithms to do scenario discovery over that entire set. And so those are just a couple of places that we've thought of thus far for using these sorts of techniques. And I think that's basically it for my presentation. So I'd hope to open up to discussion more broadly.
Let me ask you about this one. I know there's a ton of techniques on, I think, from climate and those kinds of folks. They just do compute response services and use Gaussian processes and so on. Not the more recent ML techniques do roughly the same task. So where do they fall short? And like, what are you looking for from novel techniques to improve upon, what those techniques, the state of the art is?
Yeah. So where they fell short and what we, wanted to improve upon with Persephone and FieldGen was, well, maybe FieldGen more, well, probably both of them, was that we didn't want to just capture the mean effects of the Earth system models. We wanted to make sure that we were able to maintain the variability and also kind of the covariability, so that we can predict the joint probability of both a heat wave and drought happening at the same time. This is kind of going back to just understanding these compounding effects and making sure that we don't miss out on the extremes if we're just focused on the mean climate change, which is also important, but that was the gap that we were looking to deal with.
So let me understand this. So I'm hearing a downscaling story here, where you're saying that if you want to downscale coarse models onto fine grains, you want to capture the correlations. Is that the scenario you're talking about? Or you try to say across the full distribution of parameters of GCAM was the full distribution of predictions of GCAM?
Okay, I think I'm mixing messages here. So with the Earth system models, so with the Earth system models, we want to make sure that they have a lot of process detail that will generate variability, and so the part that we want to make sure that we don't miss out on is that variability, because that leads to extreme events. For instance, in the power system, the amount of capacity that we have for electricity generation isn't determined by the mean load that you'll receive over the year. It's really defined by that peak load, and you have to have enough capacity to meet that peak load. And so that's one aspect of it. And the second aspect is the scenario discovery is because when we run these sensitivities, we don't know a priori which of these effects are going to be the most important for the impact on global mean temperature, for instance. And also for when we have these long-lived capital investments, we don't know if there's some risk, right? So we invested in a power plant that needs cooling water, but then the next year you're going to have a 10-year drought and not be able to run that power plant. And so that's kind of two separate thoughts that are somewhat related. I don't know. Was that clear?
Well, it sounds like you really want to capture more. You need a more accurate approximation to that captures more dynamics. And it sounds like you're like what response services tend to be just a bunch of points hooked up by splines, and they're just don't capture some of these details.
That's right. Yeah.
Okay, and then downscaling is really where, because I think here it's pretty obvious that you want a more flexible approximate model. But downscaling is also obvious that you want it, but I wanted to understand, how does it work? How do you reproduce, it looks like a distribution of weather patterns from the climate model, which gives you very coarse descriptions of weather?
So, okay, so you're saying that the climate models are giving coarse descriptions of weather.
And you have to shove them into so crop model, I get that you just take the what's called ag intercomparison project, figure the acronym, and you train a model, like just toss a neural net at it to give the input output behavior, or lookup table, that's clear.
Yeah.
But you still have to drive it with a weather sequence.
That's right. So those weather sequences, well, okay, those are going to be within the sensitivities that were run in the agricultural model intercomparison project. But ultimately, that weather signal is going to be kind of in the under the umbrella of some RCP climate change, climate future scenario. And so, right, like, climate is not the same as weather. And so, yeah, I can't say exactly, how they accounted for that. I'm not sure.
So that might be another conversation to have, just how, because concretely okay, I know crop models. I'm not sure how your approximation works, but if you run a DSAT, it's going to need the history of the weather for a month, or really the whole growing season. Right. And then it's really important to get at least variability between rains. Like, it's not the average rain; it's the gaps between rains. Also, to get some distribution of those histories out of the climate prediction, which is way coarser than that in time and space. So that's right. I was curious how that worked and how close you got.
So that wouldn't be something that that problem wouldn't be something that we we address directly. Instead, we're kind of we're relying on this database of results to have design their sensitivities in such a way to capture that.
You mean in the modeling intercomparison project, their database?
Yeah, that's right.
Also, maybe I'm confused. Does the database take weather histories as input, or some coarser aggregate?
So my understanding is it would be some coarser aggregate, but they would have to do something to make up the difference. And so what I guess is they would say, okay, well, assume that rain events are happening X times more frequently or less frequently, and they would have to develop sensitivities around that, and they would run their model for each of these various crops and different different grid cells around the planet.
Okay, and then FieldGen provides downscales what the climate model says to whatever that input is.
Yes, although so I should be clear that FieldGen is a model that we've created. I don't know that they use it. Maybe they have something similar. Yeah, I didn't necessarily delve into the details of that project.
Okay. No, I think it's something, I'm looking at FieldGen. It's just on GitHub, so it's really convenient.
Yeah. And I can also share the model documentation paper. Maybe I'll send that email for both Persephone and FieldGen. And those will definitely have all of the details in them.
Cool. So does anybody else have questions? I think everybody in the call, yeah, I think they're happy. Then let me ask you like a bigger question.
Sure.
This is a simulation of the whole world.
Right.
How the world only has one history. How do you tune it so as to be close to realistic, given the fact that there's only one history to tune from?
Yeah, that's a very hard problem. You know, for some things we have enough data to you know, do like Monte Carlo analysis. Analysis to you know, choose the, you know, various parameters that we have in our model to try to replicate this. But for a lot of the parameters in here, you know, we have to it's not only global in scale, but it's also, you know, considering all these different sectors, and the data just might not be there. And so we have to basically just look at the literature and just, you know, choose values from literature. And so they're highly uncertain. And so, you know, sensitivities is just kind of the name of the game for us on a number of fronts.
Okay. So then are there local predictions you can, I mean, the global predictions, there's only so many of them, but there should be a lot of local data sets to tune your models, right?
Yeah, that's true. And the question that we struggle with is there something about, you know, we're based in the United States, right? And so we have opportunity. We have much more opportunities in the U.S. than we do than in other parts of the world. And what we struggle with is, are we biasing our model by using these, you know, localized data sets?
Yeah, that's fair. And
yeah,
like if any machine learning technique is going to have that even double because it doesn't have nearly as much prior information.
Yeah.
No, this is very clear to me. This is actually like a really cool, comprehensive tool.
Yeah, thank you.
All right, well then, yeah, I guess if there's no questions, then people who are here live, yeah, thank you very much. This was fascinating. Thank you, Pralit.
Okay, and I will share with you the links to the model documentation papers for some of these models here.
Sounds great. Yeah, and I'll forward all the, you know, your slides and the recording to everybody else at Google. Thank you.
Yeah, and of course, feel free to also email any further questions that you have.
Absolutely. Well, thank you very much. Have a great rest of your day.
Yeah, thank you.